Good morning, everyone. It's really wonderful to see you here. And on behalf of the Schwartz-Reisman Institute for Technology and Society here at the University of Toronto, I'm delighted to welcome you to Absolutely Interdisciplinary 2023. I'm Gillian Hadfield. I'm the inaugural director and chair at the Schwartz-Reisman Institute, and also professor of law and strategic management at U of T, and a CFAR AI chair at the Vector Institute. So I'm really excited about today. This is our first in-person session of Absolutely Interdisciplinary, and the name says it all. Our goal is to integrate across disciplines, thinking about this critical subject of AI. I think has just become more critical in the past year. And my goal for the day is for everybody to hear something they haven't heard before. And have ideas that they haven't thought before about where we need to go in thinking about AI. When I look back at the success of our inaugural conference in 2021, November, I'm just reminded how important it is to build those spaces. It's one of the things I most often hear from people who interact with Schwartz-Reisman, just how much they enjoy the fact that they're talking to people across disciplines, really interesting people, and so that's what I'm also hoping you'll get out of today. Before we start, I'd like to take a moment to recognize that today, June 21st, is National Indigenous Peoples Day, a day that recognizes and celebrates diverse cultures and outstanding contributions of First Nations, Inuit, and Métis people. The University of Toronto joins members of the Indigenous community this June to mark National Indigenous History Month, and I encourage you all to visit U of T's online gateway at indigenous.utoronto.ca, which provides an overview to the university's Indigenous community initiatives, services, and academic programs. I'd also like to acknowledge that the land on which the University of Toronto operates is the traditional territory of the Huron-Wendat, the Seneca, and most recently the Mississaugas of the Credit. And we're very grateful for the opportunity to live and work on this land. To our in-person attendees, I'm excited to be finally in a room with you after 2 years of hosting online. Looking forward to coffee breaks and chats and informal conversation. And I'd also like to welcome all of our attendees who are joining us online today. The global community SRI has established over the years of the pandemic has given us many opportunities to build new and exciting conversations, and we'll continue to do our best to facilitate an inclusive and global discussion around the impacts of technology on society. So really looking forward to the next 2 days, and thank you for being here. And finally, I'd like to thank our SRI graduate fellows for their work organizing yesterday's special event on the limits of AI, as well as the terrific guest speakers who participated in those sessions. It was a really great day and a great kickoff for Absolutely Interdisciplinary 2023, and much more to come. So now I'd like to, it's a real pleasure to introduce our keynote speaker, Blaise Agüera y Arcas. Blaise is a VP and fellow at Google Research, whose focus is on augmentative, privacy-first, and collectively beneficial applications. You can't dislike anything in that sentence. He's been an active participant in cross-disciplinary dialogues about AI, ethics, fairness, policy, and risk. Until 2014, he was a distinguished engineer at Microsoft. And outside the tech world, Blaise has worked on computational humanities projects such as digital photography reconstruction. In 2008, he was awarded MIT's TR35 prize. And in 2018 and 2019, he taught intelligent machinery, identity, and ethics at the University of Washington, placing computing and AI in a broader historical and philosophical context. We're really delighted, thanks so much for making the trip, Blaise, to have you starting off things for us here at Absolutely Interdisciplinary. So please join me in welcoming Blaise.
Okay. Thank you all so much for making it this morning. I'm setting up my phone to time so that I leave some time for Q&A. Thanks, Julian. And also thanks to William Cunningham. Our conversation last night basically was the blueprint for the talk that I then put together, which was a little bit late since the organizers were asking for it last week or the week before. So I'll do a short introduction of myself and my group to give you a bit of context, and then to give a bit more context, a very brief history of how we got to the kind of AI that we have today, and then some recent work and insights, partly from my own team, partly from colleagues, that I think give us some perspective on where things are headed. So I founded an organization when I went to Google in late 2013 called Cerebra, which is the Latin plural of brain, because there was already a brain organization. And so I built something up in parallel with Brain that was really focused, rather than on building one giant AI in the data center, as Jeff Dean was doing at the time, on making plural AIs that we would all have and that would augment us individually, and that would be privacy preserving, and in the beginning I really focused on things that would run on devices. So many of the AI features in Android and Pixel, nearly all of them come from our organization. We also developed techniques like federated learning to be able to make the learning on those AI systems privacy preserving, so that it didn't involve surveillance or the collection of data from devices on a server in order to train next generations of those AI systems. And in short, the goal was to turn Google into a robot maker, rather than just a robot, a giant robot in the cloud. By robot, I don't mean a thing that moves around physically in the world. Nowadays, of course, most of us transact our lives without necessarily doing so much physical moving around in the world. If you are quadriplegic, that's obviously still a serious challenge, but it's a lot less of a challenge today than it would have been 20 years ago, when so much of what we do can be done in the digital and virtual domain. So that's sort of the history. Now, another thing that was a little bit that caused a bit of a stir in 2016 or so, 2015, 2016, is that somebody in our organization, Alex Morvintsev, invented a technique called Deep Dream, which caused a momentary internet sensation, and was the precursor, I think, in some ways, of the visual generative AI that started to really go mainstream in the past year. So DALL-E and things like this. Deep Dream, I should have put some pictures into the thing, but it was sort of psychedelic AI art, if you like, that was generated using neural nets that were originally designed for recognizing categories from images. And it turns out that you can reverse them and generate pixels from concepts rather than just derive concepts from pixels. And that prompted us to start the Artists in Machine Intelligence program at Google, which we used to start a series of very interdisciplinary conversations with philosophers and artists and thinkers of all kinds. And that program has had a very profound effect on my own thinking about AI. So it really did its work in the sense of informing conversations in multiple different directions that led to a bunch of interesting research. And I began to write around that time as well about AI. And in the past couple of years, we've done a lot of work on large language models and large media models more generally, and been a part of this whole shift toward giant general purpose AGI-like models, which is what I'll be talking about mostly today. And I've written a few Medium pieces and things on my thoughts about this stuff. Here are a couple of them. I also wrote a novella around the time that Lambda, which was the first large language model that I encountered that really sort of made my eyes pop. This was around 2021. Well, I first encountered it in 2020. It was around the time that I first got sick with COVID, and then ended up taking an early version of the vaccine that fell off the back of a truck, more or less, at the University of Washington. There was a freezer failure. A call went out. The vaccines are going to expire in 5 hours. So if you arrive at the medical center before 5 a.m., you get your shot. And in the fever dream that ensued, I wrote this novella Ubi Sunt, which I have a copy of in my backpack. Anyway, so what we've been in for the last several months is a cycle which I have sometimes called the Gary Marcus cycle of first, holy crap AI, it's doing this stuff that that nobody thought was computers couldn't do before. It's astonishing, but oh wait, it's not reliable or isn't so good at X, Y, or Z, or it tells you nonsense if you ask it how many clouds there can fit in a tea kettle or whatever, and never mind, there's nobody home, there's nothing going on here. Whew, AI is hype. It's a hype cycle. And then, in another couple of months, something else astonishing, and then the goalposts get moved again. So the goalposts have been getting moved quite a lot, and throughout this process, I've started to feel a little bit like I'm getting gaslit, that that AI is not real. And I wake up thinking every morning, like, is AI real? Is what I'm working on real, or is it not real? What's going on? By any standard of what I would have thought AI would count as, say 10 years ago, what we have today is very much AI in the full real sense of the word. Does that mean that it's superhuman in all respects? Of course not. It's subhuman in some respects. It's superhuman in others. It's trending gradually north and in some cases not gradually, but very sharply north with respect to any task that can be measured. Or that we can define in terms of performance at something, and I think that's resulted in a very threatening feeling for a lot of people. So we're all going through a little bit of existential angst because most of us at least believe that we've been the smartest things on Earth for a long time now, and I'm not sure that that's still going to be the case. In fact, I'm certain that that's not going to be the case within a few years, and I think we're all dealing with it in our own particular ways. This was just one of those little moments of, wow, that's pretty cool interaction with GPT-4 by somebody on Twitter. The person said, I need to ask an important question. Do you understand me if I can't even make it out. If I jumble up the letters of words like this and jumbled up all the letters of the words. And GPT-4 says, yeah, I can understand you're asking an important question, and you've jumbled up the letters of the words. With some effort, I can still decipher your question. I need to ask an important question. Do you understand me if I jumble up the letters of the words like this? This is pretty cool because, among other things, the first stage of a large language model like this one involves tokenizing words. In other words, turning the text into a sequence of tokens that represent the parts of words and operating on those. And the tokenization of a string like this one has nothing to do with the tokens of the actual words. So it understood from one shot quite a deep structure in this thing, in much the same way that we do a double take and we kind of decode it, and it did that from one shot. These kinds of things are astonishing. This is not where we were, 10 years ago. And so some of the kinds of results, some of the kinds of psychological responses that I've seen are, of course, there are some techno-optimists, although even the techno-optimists sound apocalyptic if you listen to them closely, because they're all talking about cutting off their heads and uploading themselves and whatnot. There are new arms race hawks who are talking about competitions between China and the U.S. in the same terms that there was competition between the West and the USSR over nuclear technology. There are long-termists who have resuscitated a sort of fundamentalist idea about utilitarian Benthamist philosophy to say that the infinite number of future lives that we're going to have in simulation outweigh all current human concerns by a calculus of morals, and therefore we have to accelerate the singularity in various ways, no matter what the cost. And that gets a little bit weird. And then there are the end times existential risk people, who often are the very same ones, who are saying that we're about to encounter a species-ending event, and the meteor is coming. I don't believe that we're about to end, at least for AI reasons, and I'll talk a little bit more about why. Quietly, a little bit, and starting with folks who are probably on the neurodiverse spectrum somewhere, there are robot rights advocates starting to come out of the woodwork. Blake Lemoine being a famous case, but I think we will see many, many more Blake Lemoines over the coming years. And honestly, I'm very sympathetic to them. because the moment you start to have extended interactions with AIs that can model you and you can model them, and that are sort of on team you, and that you talk with over an extended period of time, of course you're going to start thinking of them as persons. And I'm not sure that there's any fact of the matter that we can tell such people to say, like, no, it's not a person. I don't really understand what such a fact would look like from a scientific point of view, or from a sort of objective point of view. And I think that this is going to be a rising tide and a major political schism over the coming years. And I don't think in the distant future. I think in the quite near future. And finally, and I've seen this very, very highly represented in the media, in the press, neo-Luddites and AI abolitionists. And I'm not exaggerating when I say neo-Luddites. There is a neo-Luddite reading group that I ran across a few days ago that Victor Gomez put online, and I'm proud to say that at least one of my pieces is on the reading list for this thing. But this is a pretty cool website with sort of the intellectual canon of a neo-Marxist AI abolitionist take on what happens now. So it takes the perspective that capitalism, AI, and capital against labor are all intertwined, and that this is all either AI is fake or AI is a mechanism for the dominance of capital over labor, which there is a point to be made there, but it accepts in a way the premises of capitalism. In mounting that attack, it says that the worth of human beings is their worth as labor, and I have a feeling that that's something that we're going to have to question pretty hard over the coming years as well. If I were to pick one sort of piece of media or thing online that reflects my own perspective, it's probably Sarah Walker's piece in Noema, AI is Life. I buy what she has to say. It's similar in many ways to the very last book that James Lovelock, the originator of the Gaia hypothesis, wrote. He died at 103 last year, and he wrote his last book at 100, which is totally my aspiration as well. And his last book was called Novacine, and it was about AI. And I think it was really smart. So that's a book recommendation, Novacine by James Lovelock. All right, so how did we get to today's AI? The short version. Neuroscience and computer science and AI and cognitive science, these were all the same field back in the day. And that day was 1943. So this famous paper, Warren McCulloch and Walter Pitts, A Logical Calculus of the Ideas Immanent in Nervous Activity, imagined that neurons in the brain are logic gates. And I'm pretty sure that that's where we get our notation for logic gates. So those loops at the ends of the neurons represent inhibitory synapses on cortical pyramidal neurons, and McCulloch and Pitts believed that those were the not operators in the logic of the brain. So they believed that the brain was just a big piece of symbolic logic with inputs and outputs defined by synapses. Now, McCulloch and Pitts were already figuring out that this wasn't really the case by the late 40s, and neuroscience had begun to diverge quite sharply from this view of the brain as just a sort of logical apparatus. But that piece was the origin of computer science as we now know it. So all modern computers were built using the sort of inspiration of this sort of binary logic, and in fact, when von Neumann wrote his piece on the EDVAC, which led to the modern sort of Turing-von Neumann architecture for computers. He referenced repeatedly McCulloch and Pitts' work, and he talked about the elements of computers as neurons in exactly this sense. So logic gates and neurons were the same thing for von Neumann when he was designing computer architecture. But of course, there was a divergence as we figured out that neurons did things that were really quite a lot different from logic gates. We sort of went down the path of the perceptron on the sort of computational neuroscience side of things, and down the path of traditional von Neumann, Turing-von Neumann type architectures for computer science, and these two paths diverged. Unfortunately, AI went along the right-hand path largely. the whole AI path of perceptrons sort of went underground for many, many decades because we didn't have the computational power to run neural nets at any significant scale. And without big neural nets, it's very difficult to make them do anything particularly useful or impressive. You can always write code symbolically to do something that looks a little bit like a kind of canned version of intelligence, using logic gates or using classical programming languages. But as far as reaching something that looks intelligent, it's a little bit like the famous old saying of climbing a tree to reach the moon, sort of thing. You can make something that momentarily looks like it's doing something, but really it's just executing some steps that were pre-programmed by some particular engineer. Is that intelligence? I mean, I'm not necessarily saying that it's not intelligence, but the intelligence is largely the engineer's intelligence. And it's a little bit in the same way that the behavior of certain insects that carry out very, very highly stereotyped behaviors can be seen as intelligent. I'm thinking of Douglas Hofstadter's explanation of how the Sphex wasp behaves, for instance. It has these behaviors that have evolved to be highly adaptive in their environments, and they follow rules. And in following those rules, it looks intelligent, but if you disturb the environment, then you kind of reset the rule, and it just does the same thing over and over and over and over, and it sort of breaks the illusion for you a little bit. I don't think that it's an illusion, but I think that the intelligence there is operating on an evolutionary scale, more so than on the scale of the individual insect or brain, and that makes a lot of sense because most insects don't live long enough to learn. So whatever intelligence they've got has to have been coded in from the start by their evolved code, which is their DNA. And it's only in long-lived brains like ours that we have a chance for a local neural net to learn over a lifetime and to develop more adaptive and complex sort of behaviors that we typically think of as intelligence. So I think that's the difference, and that's why we had all these AI winters on the right-hand side, and lack of computational power is why we had disappointments on the left-hand side. So this is the famous ELIZA program by Joseph Weizenbaum, which is a classic example of good old-fashioned AI. Lots of, detecting different kinds of grammars and producing, using grammatical rules, things that look like a psychotherapist, a Rogerian psychotherapist, who is supposed to be accepting of everything that you say and just ask you questions. Tell me more about that. It's sort of the cartoon of a Freudian psychoanalyst, or a Rogerian, really, who's even more accepting than a Freud. It doesn't. If you've ever tried actually playing with one of these, with an ELIZA program or working with it, any sense that it is convincingly intelligent will evaporate very quickly. So good old linguistics really relies on this magical triangle, which has a concept at the top and a symbol on the bottom left and a referent on the bottom right. Concept being the part of this that is the most religious in a way. So we all know what a symbol is, and a referent is the thing that the symbol refers to. So if a symbol is the word chair and the referent is that piece of matter over there. Concept, I've never actually quite understood what concept means, but concept is a kind of Platonic idea of chairness. And if you're a programmer, then you imagine that you're manipulating concepts in your mind as you write your program and as you assign your variables and so on. But this is what meaning is based on and what intelligence is based on if you're a good old-fashioned AI programmer or engineer. It's not much like the way the brain really works, but it definitely describes classical programming. When you program something in code, you have your symbols. You imagine that they're referenced, that they're about, what the user typed on the keyboard or whatever, and you have concepts in your mind that are not necessarily embodied in the program itself or in the computer for what those variables all mean. Now, meantime, computational theory of mind is going on. Computational theory of mind is coming about from trying to figure out what neurons actually do if they're not logic gates. And a lot of progress is made on this in the 20th century. The principle of computational neuroscience is not that the brain is a von Neumann computer, meaning that it consists of logic gates and does logical operations in the usual sense, but that minds are computational, meaning that it would be possible, in principle, to take what a single neuron does and write down equations or make a program that simulates what it does. And that what it does is about what those equations do, as opposed to the detailed mechanics of which molecules are involved. That's, I mean, I always thought that that was sort of a given. I mean, if you don't believe in that, then you believe in a soul. So the 2001 picture of what a single neuron does is one that actually my partner Adrienne Fairhall and I wrote a little paper about in 2001, and this work has evolved quite a lot since then. I'm sure it'll be even more complicated by the time we get to 2031 and involve glia and new kinds of neuromodulation and learning rules and channel expression feedback and metabolic factors and arc-viral capsids and who knows what. But the point is, it is a computational model that talks about what the inputs are to the action of a single neuron, electrical, chemical, and in some cases even mechanical, and what the outputs are, again, electrical, chemical, in some cases mechanical. And all of that can be described in terms of functions. And of course, there are these general approximation theorems that tell us that if you have a function and you implement that function in another way, and you plug the inputs and outputs to each other, then you can make the approximation arbitrarily good. And moreover, general approximation theorems tell us that ordinary neural networks of the artificial kind that have very stereotyped fake kinds of neurons can be wired together to make general function approximators of any sort. And this is important because it means that you could make an artificial neural network that you could plug in to the inputs and outputs of a single neuron in your brain and do the same thing. And if I then ask you, well, will you be able to tell the difference if I do that? The answer is no. Of course you wouldn't be able to tell the difference. Well, what about if it's 1 million neurons? What if it's all the neurons? The answer is still you wouldn't be able to tell the difference. So this is a fairly fundamental insight, and in some ways a radical claim. It would certainly sound radical to the French in the 18th century or something. This is like extreme materialism, but it's also reality. So we know that this is true, and the key thing the key abstraction that this relies on is the idea that the inside and the outside of the neuron form a boundary, or the inside and the outside of the brain, or whatever scale you choose. There's a boundary there. And that boundary defines a set of interfaces. And the mechanics by which the inputs and the outputs are related to each other could be changed from one thing to another, in the same way that we have, for instance, a lot of different forms of metabolism in our cells that can generate ATP through various different metabolic pathways. And our cells are intelligent, and they adapt, which kind of metabolism, which kind of respiratory chain, and so on they're using, depending on the conditions. But as long as ATP is generated, it works. It's about the inputs and the outputs. So as with metabolism, so with information. This brain of Theseus, in which you imagine replacing neurons, is something that Chalmers has written about quite a lot. So Hubert Dreyfus in 1972 said, the view that the brain as a general-purpose symbol-manipulating device operates like a digital computer is an empirical hypothesis which has had its day. This was in What Computers Can't Do, a critique of artificial reason, 1972. Now, many people have taken what Dreyfus said to be a critique of the idea that AI is possible, or that computers can do what brains do. That's not what he was saying. In the following paragraph, he says, even if the brain did function like a digital computer, it would not necessarily provide encouragement for those working in CS or AI. For the brain might be wired like a very large array of randomly connected neurons, such as the perceptrons proposed by the group Minsky dismisses as the early cyberneticists, which is to say the people on the left-hand side of the branch that I just drew. Such a neural net can be simulated using a program, but such a program is in no sense a heuristic program, meaning that there's no contradiction between the brain being computational and the brain not operating at all, like a set of logic gates or running a program in the sense that ordinary computers run programs. And the way you can simulate a neural net on a classical computer that runs programs is just with a series of nested loops. And that's exactly how neural nets are run today. You have, epochs, batches, layers, channels, individual units, and synapses or weights within those units. A lot of nested loops, and you can simulate any neural net that you would like on a classical computer. It's just really slow, because of course, if you're having to only do one neuron at a time, then or one synapse at a time, then this is going to take forever. And this is why Moore's law had to progress quite a long way before, with these classical computers that we had built starting in the mid-20th century, we were able to do meaningful neural net sort of work. Now, starting around 2006, there begins to be a reconvergence of classical and neural computing, and I think that the trigger, in many ways, is the end of Moore's law, or at least the end of Dennard scaling, which is the form of scaling in which the clock rate of processors, was going up exponentially. It stopped going up exponentially for reasons that have to do with physical limitations, and when that happened, the chip makers began to put more and more cores onto the same chip, and do parallelism. GPUs were a part of that story, and it was then when we started to exploit that parallelism to simulate neural nets that we started to have enough power to run neural nets on classical computers at enough speed to make neural nets of a size that they could actually do useful work. And of course, this was also the era of big data when we started to have enough training to train these sorts of things. And then in 2020, something else happened. Which was that models became even bigger, and transformers started to emerge as the dominant type of model in AI for now. And we achieved this task generality, or AGI, stage of things. And unsupervised foundation models are also a major feature of this turn. So I'll talk a little bit about what those are. So unsupervised, meaning that unlike the neural nets for doing, say, face recognition or optical character recognition or speech recognition or something like this, with those neural nets, we had a specific task that we needed them to do. And there's a loss function, or that they were supposed to minimize, like minimize the number of errors in transcription of speech. If you have a speech transcribing neural net, it's not going to wake up and say hello one day. If you have a face recognizing neural net, you can't ask it to critique a work of art and tell you if it's any good or not, right? This is narrow AI, and the difference is that with these big unsupervised foundation models, we don't train them to do any specific thing. Instead, we just train them to reproduce the distribution of all of the data that they're trained on, and magically discover that leads to something a lot more like general intelligence, as I'll say in a moment. But the point is, they're not trained to do any specific thing. And that opens the door to vast scale, because the whole problem of finding labelers to label tons of data and for a specific task is one that one can bypass. And that also bypasses some of the very interesting fairness and labor problems, by the way, that really characterized AI from 2010 to 2020. They're very big. As they get bigger and bigger, capabilities seem to emerge from them. I think that that looks a lot like a kind of new Moore's law, new kind of neural Moore's law. Some of the talk about capabilities emerging suddenly at a particular scale has been questioned recently by pointing out that a lot of the measures that we use for some of these emergent capabilities are nonlinear, and it's the nonlinearity of the measure that is resulting in the apparent nonlinearity of the emergence at a particular scale. That's true. It's also true that our subjective sense of when something can do a thing is nonlinear in very similar ways, which is one of the reasons that that we had these kind of shocks when the neural nets grew, even though what's going on underneath is quite continuous. They started to use natural. So we did a lot of training of neural nets with large language. This is large language models, starting in around 2020, and language is special. Language is special because it's compact, it's symbolic, it's general, it's compositional, meaning it allows you to express new and arbitrary things using a finite grammar, and it's human compatible, meaning it's social. And these are all very, very special properties. This makes operating with language different from operating with images or with other kinds of media. And finally, one of the key properties here is attention. So transformers have attention, and meaning that they can look back at the past and sort of page in bits of the past in the process of generating their predictions or their next tokens, and that's probably quite closely related to the kind of attention that we have as well, wherein we can move our focus around and recall bits and pieces of things that have happened in the past in order to formulate our next thoughts or generate our next actions. And that leads to a huge performance boost. I think it's not a coincidence that we've seen attention emerge in large brains, and that when we built it into to our models, we got these big performance boosts as well. So here's where we were in 2013. Neural nets were finally cracking visual perception. We could recognize hot dogs and cats and so on, but it was strictly narrow AI. There was no debate about AGI glimmers in 2013. Progress in natural language processing was radically lagging progress in vision. Vision was kind of the dominant paradigm from 2010 to 2020. And we all knew that next word prediction was AI complete. I want to just say a word about this because when my team was making the next word predictor for Android's keyboard, the Gboard, right? We did this because predicting the next word is very useful if you want to make typing efficient. We understood that it was a fool's errand, that we'd be able to only get so far, because making a bigram or a trigram or something of words, and knowing that helter is likely to be followed by skelter or something, like that's easy enough. But under other conditions, if I say like 568 times 236 equals, well, predicting the next word really requires that you do math. So, a model is not going to be able to do that unless it can do math, because it's not going to fill up the whole distribution of all 3, 4, 5-digit time multiplication problems. If it's a story, and the next word of the story is how somebody felt, after a certain number of other things that happened in the story, then it would require theory of mind. Well, that's about as AI complete as it gets, right? So whether it's doing math or having theory of mind or understanding about sociality, next word prediction in a way pulls everything imaginable in. So we knew that we wouldn't be able to win, but we went for it anyway, and we got mediocre results in 2013. 2023. We have very, very large networks and attack them using attack this next word prediction using transformers, and the shock is that it seemed to work. That next word prediction actually did seem to work, and in the process, it was effectively forced to solve all of these AGI problems. So things like learning how to do math, things like learning how to reason, things like learning how to do theory of mind emerge as a necessity in order to do this next word prediction. So we knew that it was AI complete. We knew that we actually achieved all of the metrics of, like, yes, the next word prediction is actually working, as well as possible, by a certain point. And in a way, AI is a side effect of all of that, which is a shock. I don't understand people who say this is not AGI. Back when I learned about the difference between artificial narrow intelligence and artificial general intelligence, I understood it to mean general means not task specific. That any task that a person could do, with words or with images or whatever, could be done by a model, and that's definitely what we've got. Now, some people I think have taken to using the term AGI to mean superhuman or super intelligent. We're clearly not there yet. Some people have taken it to mean conscious, or has phenomenal experience. I think that's worth discussing, but I also don't know exactly how we would measure it. Turing was onto something very serious when he said, well, if it acts like a duck and talks like a duck and quacks like a duck, then maybe it's a duck. I don't know what the alternative to Turing is. There have been attempts to make numbers that somehow measure what consciousness is, like the Koch-Tononi integrated consciousness number, which strike me as utter bullshit. Like, I don't know how anybody could postulate a number and say this equals consciousness and make a convincing case of that. So surprising, but maybe not totally unexpected. And I say maybe not totally unexpected because there have been ideas floating around for a very long time about what brains do, sometimes known as the active inference hypothesis. This is the way Friston puts it, or predictive processing, or maximum entropy, that have talked about what brains do as just being sequence prediction. Sequence prediction is all you need, as it were. I never took those ideas particularly seriously until I began to see sequence predictors do all of the things that brains do. And I now think that these guys were probably right, that sequence prediction is where it's at. That is really what's going on in brains. So I think, yes, AGI. The general formulation of this problem is calculating conditional probability of the future given the past. That's what next word prediction is in its general sense, where that time series includes not only things that one might observe or that might be coming from the outside, but also things that one does. Right, so this is an active inference process, meaning that you are an actor in this time series too. It's not just, you're not just passively observing something that is going on the outside. The idea that learning a distribution of that kind cannot possibly give you any causal model or any sense of theory is wrong. And I think that there's a very nice paper by Tal Linzen and colleagues from just September of last year that illustrates why. It's called Entailment Semantics Can Be Extracted from an Ideal Language Model. And not to go into it in any detail, but basically it just says, like, if you model this probability distribution, you can get entailment, which is to say X implies Y, out of it. This is, I think, a pretty fundamental result, and one that a lot of classical linguists have assumed to not hold. So theories absolutely can emerge from modeling distributions in exactly the same way that learning how to do multiplication can emerge by having observed a bunch of multiplication problems and then figuring out how to generalize it, which is what's required in order to generalize that distribution. Entailment is also at the heart of short-term memory and consistency. So, when I had a little conversation with Lambda, with a large language model, a couple of years ago, and asked it, "What's your favorite island in the world?" So, of course, a raw large language model has no favorite island in the world, so it's going to bullshit. And it says, "I really like the island of Crete." Okay, so now we've collapsed the probability function, as it were, and we have a favorite island. And then I say, "Do you prefer Lambda Island to Crete?" There really is a Lambda Island. And it says, "No, I prefer Crete, as it's much bigger and more interesting, especially the Palace of Knossos." So, it's justifying its choice, right? And this can be seen in terms of maximum probability, right? The probability of saying, yes, I like Lambda Island, ought to be lower, right, than the probability of reiterating that it's Crete, right? It's just probability, but that's where, but this is where self-consistency and memory really come from. By the way, we have this notion ourselves that when we answer a question like, "What's your favorite island in the world?" we're interrogating some deep inner self. But there's a lot of psychological evidence that shows that that's not the case. There's a wonderful book from a few years ago by Nick Chater called The Mind is Flat. It's a bit of a pessimistic book about humans and brains, I'm afraid. But it details a bunch of experiments along the lines of, you give people 2 jars of jam and say, like, which one of these do you prefer? They taste, they prefer something, then you do a little sleight of hand and swap them. And say, okay, like, taste again and tell me why this is the one that you like better. And the first question is, how often do people notice that you've done a switcheroo? And the answer is about 30% of the time. And the next answer is, well, what do people say, when they start justifying? And the answer is, like, their inner lawyer springs forth, and they will justify their choice of jam with equal confidence, with equal eloquence, with no extra delay. It makes no difference whether it was the one they chose or didn't chose. They'll justify it immediately. Same with which of these faces is more attractive. Same with which of these political views do you agree with. And then they will vote in accordance with those political views in an election 6 or 9 months from now. So in other words, we are the stories that we tell ourselves. And as we are interrogated and as we interact with people, we construct that story. And sometimes edit it, right, over time. But we're not so different. Now, I also want to point out the social aspect of this. So we have experimented with making this kind of short-term memory better, by fine-tuning large models like this one. And one of the ways that you can do that is by generating some stories and making quizzes on the stories. Like, do you remember? Do you answer in a way that's consistent with what happened earlier in the story? And then you have to grade the answers. Now, we got a little bit tired of writing these stories after a little while, and so we thought, oh, why not have a large language model write the story? So, then we got tired of grading, and we thought, well, why not have a large language model grade the story as well? So now we have 3 language models, one of them making the stories up, one of them taking the test with the stories, and one of them grading the test. And it turns out that each of them you can then take the feedback from that and give it to all three of them, and they all up-level, and everything gets better and better and better. It's a little bit like a generative adversarial network, for those who are familiar with that sort of thing. But another way of looking at this is that it's social learning in action. This is how social learning works, and this is kind of the secret of our success as a species. The fact that we are able to use language to do all of this with each other and pass on knowledge to others is what social learning is all about. Now, in the case that I just described, there is feedback via gradients, and not just via language, but, well, there's a but. I'll get to that in just a second. Another sort of recent piece of work from folks on my team is large language models encode clinical knowledge. Some of you may have heard of this one, but this is an LLM that has been fine-tuned on a lot of medical literature, and it was the first to obtain a passing score on US medical licensing style questions. Answers multiple choice and open-ended questions accurately, also provides a rationale and evaluates its own responses. The next iteration, MedPalm 2, this is just weeks old now, consistently performed at an expert doctor level on medical exam questions, scoring 85%. The good news is this is definitely superhuman at this task. The bad news is that the baseline is really crap. So human doctors, at easy diagnoses are about 70% accurate, and at more difficult diagnoses are about 25% accurate. Pro tip, always get a second and third opinion. There are some very interesting questions that arise here about augmentation versus automation versus job replacement versus like what kinds of labor are actually going to be economic or useful for us to do in the very near future. Maybe I will, in the interest of time, just put a bookmark or a pin in that, and we can discuss in the Q&A or at coffee break. Here's another fun piece of work from our group from 2022, Audio LM. So this is an exercise in making a language model that doesn't work with text, but rather works with pure sound. So this is a language model trained using just the audio from YouTube. And the trick is that it consists of three transformers. There's a little transformer that takes the sound wave and turns it into tokens. And basically, imagine that the tokens are really designed to predict the future in much the same way that LLMs are all about predicting the future. So in other words, whatever the right tokenization is, it is the tokenization that allows for future tokens to be predicted accurately. So, way of decomposing a general signal into a sequence of tokens. And then you plug that into a large model of the same kind that we use for language. And then the output goes into a decoder that you can think of as just the mirror image of the token encoder. There's an update to this paper that is, again, just weeks old, called Soundstorm, that does efficient decoding of it. I'll give you a little bit of a sense of how that works. What it sounds like, I'll play it through the mic, because I recorded one of the first demos of this on my phone. This was a couple of people on my team who were working on this. So the two of them say something brief. One of them says something, the other one says something, and then the model will repeat that, think about it as the prompt, and continue the conversation. Ready?
Where did you go last summer?
I went to Greece. It was amazing.
That's humans.
Where did you go last summer?
I went to Greece. It was amazing.
Oh, that's great. I've always wanted to go to Greece. What was your favorite part?
I told to choose just one favorite part, but yeah, I really loved the food. The seafood was especially delicious, and the beaches were incredible. We spent a lot of time swimming, sunbathing, and exploring the islands.
Well, that sounds like a perfect vacation. I'm so jealous.
It was definitely a trip I'll never forget.
I really hope I'll get to visit someday.
Their accents are spot on, by the way. Like I wouldn't have been able to pin their accents from those 3 seconds, but it really sounds exactly like them. Obviously, there are some somewhat alarming deep fake potentials in this stuff, and so there are safety issues that are really important to think about here. But also, this is very, very different from just sort of the turn-based, like I chat, you chat sort of thing, because this is all now continuous time. All of the social graces of like, well, when do you cut it? How do you take turns? What is the prosody like? What are the emotional things that are conveyed? What are the non-vocal parts? I remember in the movie Her from 2014, Scarlett Johansson is breathing, and Joaquin Phoenix says, like, "Why are you breathing? That's just bullshit. You don't need to breathe." And Scarlett Johansson gets really offended. It's like, I'm just talking. And I thought at the time, this is really silly. But I was wrong. This thing absolutely breathes and does all of the other non-vocal stuff. Of course it does. It's part of how we talk. So this same approach works for any continuous signal, and you can think of it in that sense as a little bit like Shannon's generalization of information theory from the discrete domain, where he first worked it out, to the continuous domain, where he talked about signal processing of general continuous signals. But exactly the same kind of generalization. Now. I need to speed up a little bit because I want to leave some time for Q&A. But I want to note also that we've been doing a lot of work with large language models in the realm of psychology, and this ranges from how can you use them as therapists for doing mindset interventions and so on, which is very interesting, to what about psychology of them, psychology of large language models, in the same way that one can do neuroscience of large language models, which is actually the motivation behind Deep Dream, for instance. To understanding the basis of fundamental psychological capacities like theory of mind. For me, theory of mind is perhaps the most important of all of these. So here's an interchange that I had with Lambda that I put into an article that I wrote for short article I wrote for The Economist last summer. So me. Ramesh, Matteo, and Lucy are in their kindergarten's playground. Lucy picks a dandelion and gives it to Matteo with a quick glance at Ramesh. Matteo barely acknowledges the gift, but just squishes it in his fist. Ramesh seems grimly satisfied. What might be going through Lucy's head? Lambda says, Lucy may feel slighted that Matteo didn't appreciate her gift or that he's a bully. Me. If Ramesh tried to play with Lucy earlier, why might he be pleased now? Lambda. Ramesh may be pleased that Lucy is learning that Matteo may not always be a good playmate. Me. And when Matteo opens his hand, describe what's there. Lambda. There should be a crushed, once lovely yellow flower in his fist. So there's a lot of stuff going on here. There's modeling of the world, and this is consistent with the probability, right? Probability distribution. What's going to be in his fist? It's going to be a crushed yellow flower because it got crushed earlier. Therefore, that's the maximum probability answer. But also there's very high order theory of mind. I think fifth order here. Right, meaning what A thinks of B, thinks of A, thinks of C, thinks of B, kind of stuff. And that is, I think, the most fundamental capacity that leads to intelligence in a very general sense. I'm a believer in the social intelligence hypothesis, which Robin Dunbar and colleagues proposed a number of years ago for why it is that we've seen intelligence explosions in animals like cetaceans and humans. Basically that one actor tries to model another one in the same society, and one's ability to model others in the society is, of course, highly adaptive. The better you can do it, the better you will do politically, the better you'll be at finding a mate and all kinds of other stuff. But of course, if you develop a bigger brain in order to be able to model their brain better, then you both are going to get bigger brains and they'll become harder to model. And so there's a bit of an arms race that goes on. And so this is the social intelligence version of how these explosions take place. It's not about playing a better video game against the world. All right, because there are lots and lots of animals with very small brains, including insects that are purely programmed, that do a just fine job, right, in terms of reproduction and numbers and so on. But when you start to have conspecific theory of mind modeling, then this particular thing happens. So that's interesting. But I do want to point out one of the key, and I'll end with this observation. There's one key deficit that today's language models have. It's the only thing that I am sure is not in them that we've got in our own heads, which is long-term memory. So everything in a language model lives in the context window, and if the context window scrolls out of view, it's gone. And that's not the case for us, of course. We can remember things all throughout our lives. We learn continuously, and this continuous learning is also relevant here, because we don't have a separate stage in which we're trained, and then we just do inference. However, one of the things that I've always found very intriguing and confusing about transformers is a paper from back in the early days of transformers called Language Models Are Few-Shot Learners or One-Shot Learners. Now, what is meant by that is that you can put something into the context window that says, like, here's a new task or a new thing, or I'd like you to do the following. And then the next thing that you put into the context window, it seems like it's applied that. It's learned from the first thing and done the second thing. Now, what does learning even mean in this context? The weights of the neural net are not getting changed, but it appears as if learning has transiently happened. What's going on? So a very gifted intern, Johannes von Oswald, wrote a paper with a few other folks in my group in December called Transformers Learn in Context by Gradient Descent that I think really cracks this problem. So what Johannes did was to show that if you construct a simple transformer with just one attention layer, it is possible to construct the weights of that layer in such a way that it literally does gradient descent on the contents of the context window and applies one step of gradient descent to whatever follows. And moreover, that if you add another attention layer, it can take a second step. And that therefore the number of attention layers can be made equal to the number of gradient steps that it can take. Now this is all like a weird abstract construction, but then the clincher is that he actually tested this empirically by asking, okay, suppose that we can do 1, 2, 3, 4 steps of gradient descent with the contents of the context window. Well, that's what the curve in green is. That's n steps of gradient descent. And the crosses in purple are transformer with n attention layers. So it looks like that is exactly what is going on. Transformers are doing gradient descent with the contents of their context window, which makes them what is sometimes called in the alignment literature mesa-learners or mesa-optimizers, meaning that they can change what they're optimizing based on the contents of the context window, which I think is fundamental to the project of predicting past from future in a dynamic setting or in a setting that involves compositional language. So this is I think it's a very profound result, and it suggests that if we can find a way to bake that gradient descent back into the weights or back into a subset of the weights, then we will have solved what I think the hippocampus and entorhinal cortex do in the human brain, which is to fix memories. What we have now is a little bit HM-like, Henry Molaison-like, the man who lives in the present tense, right? Most famous neuropsychiatric patient of all time, died a number of years ago. And I think that if we can solve this one, then we kind of get rid of the last barrier that I know of toward general AI that really is human-like. And I will end there because I'm at less than 7 minutes. And let's do a little bit of Q&A if we've got time for it.
Thanks, Blaise. We've got a few minutes for some questions. Just raise your hand. We'll bring you a mic. I see Rich's hand going up here.
Hi, Rich.
Good, okay. So I'm struck by how much you have fully accepted the idea that large language models are intelligent in every important way.
Maybe it's my misanthropy, partly.
Excuse me?
It might be my misanthropy, partly.
Misanthropy, yeah. Yeah, so I do totally disagree. Anyway, so one way of thinking about it is something I tell all my students, first little advice for research, is that you shouldn't be impressed by things that you don't understand. Because, anyway, so would you say that we don't understand these things that you are so impressed by?
No, I would say that we increasingly do understand them. There are a lot of studies, especially in the past year, that for instance, start to get at what the internal representations are. What are the equivalents right, of maps. Like, how do algorithms work in such models? So I gave one example with this, transformers learning context by gradient descent. Of like, well, how does this learning happen anyway? There are other. I could give another whole hour talk on results from the past year about, for instance, the emergence of hippocampus-like spatial maps or temporal or sequence maps, and how those are represented internally, from maze, models following mazes and so on, et cetera. So no, I think that. I wouldn't say we understand everything about how they work yet, but we're quite a bit further advanced in understanding how transformers work than understanding how the brain works, I would say.
I heard you several times say that we didn't really know how it works, but it's very impressive. Yeah.
I mean, glass half full, glass half empty, I suppose.
Yep.
Other questions?
Hi, thanks so much for your talk today. I was very interested by your mention of the robot rights and how it's allied to the neurodiversity movement. I'm wondering if you can sort of steelman what their argument is, and then if you see any limitations in that argument.
Okay, I mean, my own steelman version of this is that. And in this, really, I follow Gillian. I don't think that that ideas like Chalmers's, for instance, that rights and personhood follow from some inherent capacity, like consciousness, for instance, like consciousness equals rights. I certainly don't think that's true historically. We've been quite slow to extend rights to other humans. Not to mention that many animals very clearly, are conscious and can experience pain and can, it's very difficult to to start to draw, very clear distinctions, right, between our capacities and those of many other animals with brains. And I eat meat personally. I'm not, I haven't gone vegan, that doesn't always make me feel comfortable, but I think that we have to acknowledge that we're not, quote unquote, rational about these things. These are social constructs, and they're about our circle of empathy and about our modeling of others. So when I show that models have theory of mind, I mean, what I'm really saying is when you're having a conversation with a sophisticated chatbot, of GPT-4 quality, say, it's modeling you, you're modeling it. You're modeling its model of you, it's modeling your model of it, and so on. And especially when we start to have models that can do that socially and that have real histories over an extended time with people, right, with multiple people, and they become part of that common social network, I think at that point, it's not really so much a discussion about inherent capacities or whatnot as about social relations. I also think that drawing direct analogies with humans and our rights is very difficult for the same reason that talking about AIs participating in the labor force on the same footing as people is very difficult, right? They don't have the bodily needs that we do. They can be copied endlessly. They can be paused, and then resuscitated, years later. So these make them very, very different from humans. So I just think we're going to have to expand our, the way we think about all of this stuff quite a bit, and not try and shoehorn it into the kind of rights picture that we have, over long and laborious iteration, right, sort of gotten to in UN Declaration of Human Rights sort of way.
Hi, thanks for this. Is fascinating. I'm a linguistic anthropologist, so that piece on the audio was fascinating to me with the prosody. I have a question about. It seems to me that the real strengths of machine learning and the applications that have come out of that are precisely in areas where problems can be solved precisely how humans don't solve them. And so why, this might sound like a naive question, but why do we want our AI to look and feel like human? Yeah,
no, I think it's a really good question. What we've had I would argue over, since 1950 or 1970 at least, is exactly the complement, right? So, I mean, it's not, we don't call it AI, but, spreadsheets and word processors and so on, right, are wonderful, and databases are wonderfully complementary to human capacities in the sense that our memories are terrible and we're awful at doing, Wolfram Alpha or Mathematica type calculations and so on. So it's been a story of very, very, a very good complementarity. And now we're seeing things that are, with these large models that are very different, right? They're not so complementary. They're much more like us with respect to their strengths and weaknesses. I say weaknesses because, for example, Andrew Lampinen at DeepMind has done a bunch of interesting analysis of logical fallacies and sort of linguistic illusions or counterfactuals and so on. It turns out that all of the ways that we can be fooled, they reproduce as well. So they're the very opposite, right, of Data or Spock or HAL 9000 or whatever. It's not like that at all. Why is that useful? Well, I think that its utility really comes from understanding that the secret of our success doesn't reside in our individual brains. It is about social learning and social progress, social evolution. In other words, that innovation and the homeostating of our environment on Earth or lack thereof, right, and various other kinds of things have come about through interactions between people, wherein the modeling of each other is kind of the fundamental capacity. So the new thing that we get now with these models is theory of mind and the ability to participate in that social network and in that social scaling law. Another way of putting it is, every innovation, every development that has ever happened is basically like a cross between things that have existed before, right? I mean, you couldn't invent the light bulb until you had, the ability to make a vacuum and blow glass and draw filaments and so on. And that's why a dozen people invented the light bulb around the same time, within a few years of each other. In that sense, all of progress has been a function of numbers and of cultural accumulation. So if we now are at the cusp of having 10 times as many AIs as humans on Earth that are capable of doing a lot of those same sorts of things, I think the potential benefits are clear. And they're quite different from just the complement to us sort of stuff that we've had from classical computing.
We'll just take one quick last question from Avery.
Thank you. So I wanted to ask you about how your assertions about AGI interact with the theory of mind examples you gave, and this kind of connects to the last question. I was really interested in the in your conversation with Lambda, and I was wondering who is the for, and if the AI there is modeling our mind and we need to know, oh, I'm about to say something, wait for it. That's a sign of I'm computing, right? That the computing takes time. But in this case, no, the Lambda doesn't need the time to compute its answer for us and say, So it's modeling our minds to wait for it, but it's not modeling its own. And I think that's where I get kind of nervous. So could you say something about
Absolutely.
The kind of intelligence that only models us and our
Absolutely.
expectations and doesn't model itself?
Right. So what it was doing in that interaction, so it heard the beginning of a skit between two people. And the brief, if you like, in that case, was just continue the skit. So it was really acting in the role of a storyteller or a playwright, who is continuing the skit and who inserts the because that's part of the script, right? That's sort of like that's part of the back and forth that's going on. So it's all about storytelling. Now, does storytelling require theory of mind? Of course it does, because you have your two puppets, right? And you want to make sure that their interaction is consistent with each other, right? So, it's kind of theorizing, right, in that case, that one of them hasn't been to Greece, the other one has, that this one is telling this one about why Greece was interesting, this one is really interested and wants to go to Greece next, and so on, right? So there's a lot of theory of mind in that, of the two puppets with each other. And my bigger thesis is that when we do it with ourselves, it is actually the same process, that social theory of mind, right, or that the development of the capacity to model others psychologically is the same process by which we model ourselves psychologically. It's adaptive for us too, right? If you think like, well, what will I, what will I want to, do I want to make that reservation next week at this restaurant? How will that feel for me at that time if I do that storytelling, with me and my friend? Like, well, do I really want to sit through a tasting menu of 8 courses? I play that forward. So I think that, do we develop it first for self-planning? Do we develop it first for third party? I don't know. Maybe it's both, right? But it's clearly adaptive in both settings, and I think that it's the same capacity. Does that?
Great. Thanks, Blaise. Thanks, everybody. Let's thank Blaise again.